Good afternoon, everyone. Today with this video we end the topic, or let's just say we end the survey of differential calculus and we enter the survey of integral calculus. As you have come to realize, while derivatives and differential calculus had very much, if you remember correctly, had very much to do with a certain limit, and that limit represented the slope of a tangent line. And you know what this really was. The slope of a tangent was really basically an instantaneous rate of change. The derivatives or the differential calculus represented a special kind of limit, which was your slope of your tangent line, which I have said repeatedly is an instantaneous rate of change. When we're talking about integral calculus, we're looking at a symbol which looks something like this. And it continues on into this format over here. There's a specific lower and upper limit. We will talk about all of this. When we're talking about integrals, or the whole area of integral, let's just say integral calculus, we're talking about a specific limit over here, and that is a limit of sums. We're talking about basically cumulative effects over here. The sum cumulative effects of whatever it is that you're studying. When you're looking here at this symbol for integral calculus, look over here. You have this specific symbol over here which looks like an elongated S. That's a symbol for an integral. And then within that integral, if you're looking at definite integrals or integrals which are defined over a specific domain or an interval, you can say interval or domain, both are good words. Anytime you have an integral which is defined over a specific domain or an interval with a start and an end point, you can represent that over here as a lower limit and an upper limit. This basically represents where your function is being studied, or where the sums, the limit of those sums is being studied from what start to what end point. And then the f of x over here, which you see over here, which is really a function, is also called an integrand. Integrand. I-N-T-E-G-R-A-N-D. Integrand. It's the basic main part of your integral. This right here is entirely called an integral. An integral function or integral equation. Look over here, right here. This basically represents what your integral is with respect to what, in terms of you dealing with an independent variable. Independent variable. It's not a dependent variable. It'll be an independent variable. Whatever it is your function is studying, it's with regards to that. And you know, an independent variable has the ability or the power to influence the dependent variable. And normally the independent variable is presented on the x-axis of a coordinate system, whereas the y-axis represents your dependent variable, which depends on the values you input in terms of x. Your y values represent what you get in terms of the output. So this right here is your independent variable representation of this entire integral over here. You don't need to worry too much about how these two relate. Like if you have differentials and you have integrals, like what is the main relationship between them, because we're not worrying about that. What we're worrying today about is basically the concept of integrals. And you know, I've told you we're dealing with a special kind of limit, the limit of sums. In layman's term, you can also understand this in the following way. If you have a specific curve, what is the area under that specific curve? When you can come up with the basic understanding and how to calculate the areas under a curve from one specific domain value to another, your A to B, see the lower limit to the upper limit, lower limit, upper limit, and what are this curve function equation is. Once you can learn how to do the determination of the area under the curve, you can take these concepts of integrals a step or two higher and then start getting into volumes. But just like how when we were talking about derivatives, there was a derivative scheme or template you followed for the various types of functions, polynomials, trigonometry, hyperbolics, natural logs, exponentials, from A to Z. Whatever we were talking about, the inverses or the regular, just like that, there were specific templates and schemes, or like a specific procedure on how you determine the derivative of your function. Well, like that, for all of those functions, there's a specific template, scheme, or let's just say a schematic on how you will take your function type and you'll get the integral calculation out of it, or how you would do the whole process. And that whole process is called integration. The process of actually calculating an integral is called integration. And when you're calculating the area under a curve, that is represented, or that is basically exemplifying the process of integration. Today I want to talk about the whole concept of integrals, but not by using the word integral too much, but by looking at through another more basic understanding, or let's just say we're going to look at things through a more basic perspective And then when we get into the next video of integrals, we'll start actually really talking about integrals. So today is a basic video where we'll understand the concept of integrals, but without talking too much about integrals, but we'll talk about what it is when we're talking about areas under a curve, like what it is that we're actually doing. That's the crux of today's video. In my opinion, when you study the Riemann sums, you might have heard this word or you may not have. Anyhow, when you study this specific concept of Riemann sums, it actually gets into the very basic understanding of an integral, because remember, as I said previously, integrals represent a special kind of limit, the limit of sums. That is basically you're addressing an area problem. What is the area under a specific curve? If you look at things from a very basic perspective, and let's not even get into calculus for these next minute or so. If supposedly I give you an equation of a graph, let's not even call it a function. If I give you this representation, we know we have 0, 5 over here, and we have a 5, 5 over here, and we have a 5, 0, and you know we have an origin over here, 0, 0, and I told you to find the area of this. You know exactly how you do it, because here you're not even thinking about calculus at all. You know you have a length and you have a width, and you can do easily that. You have a 5 and a 5, and you know here the area is really 25. It's easy. And if I give you another thing which looks something like this, like a triangle, this right here is a true function. This may not even be a function here because of the presence of this vertical line. Anyhow, if I gave you this and I'm telling you this right here is 0, 5, and this right here is 5, 0, and let's find the area of this. You know you're looking at the length times width, the formula for rectangle or square. Here you're looking at the area of a triangle, which you know base times height over 2, and these are easy, you can do it. You'll get 25 over 2 as your area over here. These type of questions are easy. The problem arises when we're dealing with integrals is when you have curved lines, how you go about determining an area of that type of thing. If I gave you like this, f of x is equal to x squared, right over here, and I'm showing you this over here, x squared. Now if I told you from the lower limit of 0 up to, let's just say 2, the interval, how would you go about finding the area under that curve? And you could represent this in terms of this following notation: the area of this function, which you know is x squared. How would you do it? You would have to do some sort of integral process from a lower limit of 0 up to a higher limit of 2, because this will go on to infinity, but we're defining the area between 0 and 2, and you know the function is this with regards to your independent variable x. Like this right here is what we're talking about when we're talking about curved lines. They're drastically different than this. You could say, let's just draw a point over here and draw a point over here and make this into a triangle. Now we know we have a base and we have a height, and we can just use the basic triangle thing, the triangle equation. We can do 2 times whatever this height is divided by 2, and you can get an approximate representation of the area of this function, but that approximation will not be accurate because you're adding all of this extra space in between. All of this extra space between the curve and this diagonal line, your hypotenuse, you're adding that extra area which is not even represented by your function. So when we're talking about Riemann sums, we're going to use as our base function this right here, x squared, because I find this to be a very adaptable and a very helpful function to understand the Riemann sums, which we will look at next. And when we're talking about Riemann sums, we're not using them for these type of representations, though you can, but we're not. We're using them for these type of representations where you have curved lines. Remember, in the previous whole section on differential calculus, we've been looking at the slopes of curved lines using differential calculus. Now we'll be looking at areas of curved lines using integral calculus. But look, in each cases we're looking at curved lines because curved lines are not amenable to ordinary techniques. So let's get into the topic of Riemann sums. Given the framework that we'll be using x squared as our function, then we'll get into the process of determining Riemann sums. Now look over here, right before you I have 3 plots, and these are basically just the Cartesian coordinates. I'm only showing quadrant 1. The quadrant 2 and 3 and 4 in each of these cases is eliminated. I'm only focusing on quadrant 1, and all of these represent this function x squared. This is what we're looking at, you know, the x squared, the parabolic function curve over here. If I told you we had to find the area between 0 to whatever point, let's just say we're looking at from the lower limit of a up to b, who cares? We're not even looking at proper numbers over here. We're trying to develop the concept of a Riemann sum. The whole concept behind Riemann sum is you are basically, and I'm going to show you right over here in this extra graph over here, you're basically looking at a curve and you're drawing rectangle representations. Now I'm not drawing anything over here to accuracy at all, because I'm developing only the base concept over here. Now look over here, I'm drawing vertical rectangles going up to the limit of this curve. If you were to calculate individually the areas of each of these rectangles and you were to add them up, that would give you an approximate representation of the area under that curve. But now a number of issues arise over here. You know, each of these rectangles must have a length, and each of these must have a width. Well, the width part is easy. Here's my width, and the length part is over here. Now how do we actually determine the length and how do we actually determine the width? We will look at all of that. And another concept that arises over here, what aspect of this rectangle or the top of this rectangle must be touching the curve? Are we looking at, if you look at this, the top of the rectangle, we have 3 points which arise. Look over here, this little point over here, we have the other end point, then look over here right in the middle, we have another end point. We have a left end point, I'm using abbreviations here, left end point. We can be looking at this rectangle touching the curve at its left end point. We can be looking at the middle point where the rectangle touches the curve at its middle point, or we can be looking at the right end point where the rectangle touches the curve at right end point. You see, you have 3 different scenarios we have to look at. That's why I have 3 different plots over here. If you were to draw rectangles, and keep in mind, for any curve you're trying to determine the area, the more rectangles you can draw with smaller and smaller widths, the more accurate will your answer be. If you have a given curve and you only draw like 2 rectangles in there and you determine the area of those 2 and you add them up, you won't have an accurate representation of the area on the curve. But if instead of drawing 2 you draw like 5 or 10 or 100 or 1000 or even an infinite number of rectangles and you add them all those individual sums up, now you'll have a true representation of the area under the curve. But let's look over here, the left end point, the midpoint, and the right end point. If you're drawing rectangles over here using the left end point, we're going to have to be a little over here. You might not be able to see very clearly at the base, but as I come up here towards the top, you'll see only the left end points must be touching the curve. You see the left end point right over here, the left end point must only touch the curve, the left end point of each rectangle. You see here's a left end point in each of these instances, and we're not trying to draw an infinite number of rectangles here. I'm only showing you the left end points. See, only the left part of each rectangle touches that curve. Now look over here, if you're looking at only the middle points of the rectangles touching the curve, and this is all symbolic or graphical representation of Riemann sums. We'll actually get into the calculation part soon. If you're looking at the middle part, look over here, and let's focus only on 4 rectangles for each of these plots. Look over here, what happens? You see the midpoint over here is touching over here. The midpoint over here. The midpoint, well, relatively close to a midpoint. And let's, for the purposes of this graph, let's extend this a little over so I can actually fit another rectangle in here. You see, we have basically the curve going to the midpoint of the top, close to the midpoint. Here the curve is grazing the left end points. Now, how would it be if we're looking at the right end points? Right end points, you'd basically have a rectangle, and I'm going to do 4 only. You see, right end point is only being touched over here, right end point only. I should extend this out a little bit over here. Just, I know I've made this little graph inaccurate, but I wanted to show you just for the graphic representation the difference between each of these Riemann rectangles touching in terms of the left, mid, and the right end points. Here's the left end points touching left end point of each of the rectangles touching the curve. Here's the midpoint of each of these rectangles touching the curve. Here's a right end point of each of these rectangles touching the curve. What is the lesson to be learned over here? When you're looking at the left end points, you'll end up having an area in terms of your function which will be less than the true area. You'll end up underestimating your area. If you're looking at this right end point, and I didn't put REP over here, right end point, you'll have an area which is it will be overly estimating the true value. Your calculated Riemann area over here, or your Riemann sum will be overestimated. It will be larger than what the true area is. Here on the left end points, if you're using it, it will be underestimated. So what's the best method to use? It's this one right over here. If you have given enough number of rectangles, here your calculated area under the curve will actually be very close to, if not equal to, the true area under the curve. And you can only actually really equal the true area of that curve under the curve if you draw extremely large number of rectangles, or you use limits as they approach infinity. If you draw a fewer number of rectangles over here, of course you will not be equal to the true, but you'll still be better than these approximations over here. I want to show you some examples of how things play out in terms of the Riemann sums. So when you're looking at any Riemann sum, let's just say Rn, n represents the number of rectangles you're looking at. If you have a function over here and you only have, like, let's say, and I'm not showing right endpoint, mid endpoint, or whatever, you only have 4 rectangles drawn over here, 4 rectangles, you're looking at a Riemann sum of 4. And let's talk about the width over here. What's this width going to be over here? This width over here is your delta x. You know, we started here from a lower endpoint and we've gone up here to a higher endpoint in terms of the x-axis. Remember, the lower endpoint to the maximum or the higher endpoint, these are your domain values, your x-axis values. You're going from an x-axis value of a comma 0 to b comma 0. That's what we're talking about. When we're looking at the width of each of these rectangles, your formula is b minus a, your interval, divided by the number of rectangles you're dealing with. If you supposedly have an interval which is 0 comma 1 and you're trying to look at Riemann, let's just say 4, you have 4 rectangles, you know your delta x in this case will be 1 minus 0 divided by 4. So each of your widths of your rectangles will be 0.25, or you can say 1 over 4. Now I'm laying over here the groundwork for the formula that will be involved, and then I'll show you the whole schematic of how everything plays out. The actual formula is this, basically. You're going to look at the limit, and let's just say as n approaches infinity, because the maximum number of rectangles you can draw under a curve will yield you the truest form of the area under the curve, is equal to sum. As your first integer is equal to 1, going up to your nth integer is equal to the value of each interval, and I'm going to show you all of this, multiplied by the width of each interval. This right here will represent your length, right over here. This right here will represent your width, and you know area of a rectangle is length times width. But what are we actually talking about when we're talking about f of xi? What are we actually talking about f of xi? We're basically first finding an xi value. We're first finding what your specified value is. The specified value will come from which type of approximation are you using? Are you using a right endpoint for your intervals, or are you using a midpoint, or are you using a left endpoint? Any of these, whatever is the specified interval based on which type of approximation you're using, is going to give you your xi. But what exactly is f of xi? Well, if you're looking at this right over here, then you're putting in these values right into this formula, and that right here is giving you your output with regards to your specified value based on whatever assumption you're taking. So each of these values, when you put them into the function, you get an output value. That output value represents your length. You add up all of these lengths and you multiply them at the end by your width, which is represented by this formula right over here, b minus a over n. Now when you look over here at this formula, f of xi and length, which is representing your length, and delta x, which is representing your width, which I've shown you here, delta x, you can do it in one of two ways. As I mentioned, you can do individually length times width plus length times width plus length times width plus length times width, which is a more cumbersome process, or you can do all the sums of the length and at the end multiply the cumulative sum of the length by the width. And this is what I'm talking about. Look over here. If you have L1 multiplying by width for this first rectangle, L1 times its width plus length 2 for the second times its width plus length 3 times that width plus length 4 of the fourth rectangle, multiply that by width. You can just isolate W from all of these. See W, isolate the width, which is this. You can isolate the delta x and then do the cumulative sum of all of these, L3 plus L4, and that's exactly what I'm doing. You, in this formula right here, you do the cumulative sum first of all of these lengths, then at the end you multiply it by the width, which is right over here, the delta x. When I show you this in an example form, you'll see exactly what I'm talking about. But your main formula is right over here. It's going to be the limit as n approaches infinity, the sum of the specified values placed into the function, the sum of all of those specified values as you place them in your given function, multiplied by delta x, which is representing your width. The delta x is based on the difference of your upper interval minus your lower interval divided by the number of intervals you have. This right here represents your number of intervals, which in a picture form tells you how many rectangles you've drawn. Let me show you an example. And as I've mentioned before, you can use intervals based on the right, middle, or the left endpoints of these rectangles on the top. But the most and the best way of doing it is using midpoint. The midpoint of that interval is what you should also be using. Let's look at slightly a bit of a comprehensive example. If you're looking at a function which is just x squared, and you know I'm talking about x squared over here, and we're looking at, and we want to calculate the area under this curve under, let's just say from a 0 to 1 interval, and we have to calculate the x squared, the area under this curve from 0 to 1. You know what I'm talking about. I'm talking about here a Riemann sum. And how many rectangles do we want to draw under over here? Let's graphically represent what we want. We have the x squared over here, we have 0 over here, and interval 1 up to here. We want to fit 4 rectangles. Here's my first one, here's second one. Remember, the curve must cross at the midpoint, and here's my third. Drawing rectangles or drawing these pictures sometimes is hard, but you see how the curve is going to the midpoint of the top? You see here, the curve is going right here to the midpoint, right over here. That's what we're looking at. Now, when you're doing these type of questions, there are 3 things you want to note. And these are the 3 things you want to note. And I'm going to show you how I do these type of questions in my way. Because when you're doing this whole calculation, that calculation is your integration process. We're just doing it under the topic of Riemann sums. We're basically here calculating Riemann sum 4 because we have what? 4 rectangles, right? N is equal to 4. And this is, I'm going to show you how you're going to do it. And we're using the midpoint values. And you can also calculate the width of each interval is equal to b minus a over n. Over n, what's b minus a? b minus a, 1 divided by n, which is 4. Each interval must be 0.25 long. Now look over here. This is how we're going to lay it out. We're going to lay it out in this way. We're going to write an interval heading. And then we're going to write, let's say, xi over here. And then we'll write f of xi. Why am I writing xi and f of xi? Because xi is the specified value which I'm going to use based on this. And then the f of xi is what that value is when you put it into the function. If each interval must be a quarter units long and I only have 0 to 1, you know, obviously my first interval is from 0 to 0.25. My next interval is 0.25 to 0.5. And then the other interval is 0.5 to 0.75. And then the last interval is 0.75 all the way up to 1. That's how you do your intervals. The more number of intervals you have, or the higher the n values, the more accurate your value will be. But if you are using the midpoint, you'll be having a better representation of the area than versus using the right and the left endpoints. Now look over here, what's xi over here? The xi is representing what type of point we're using. We're using the midpoint. So you have to find the midpoint of this interval. You just have to bring a calculator and do the half of 0 and 0.25. If you do 0.25 plus 0 divided by 2, you get 0.125. 0.125. If you do the half of this, you get 0.375. I imagine it would be 0.375. 0.5 plus 0.25 divided by 2. Yes, and this one right here would be 0.625. And this one right here would be 0.875. Now all you have to do is plug in these values in terms of this function over here and get a value. What's 0.125 square? Let's do 0.125 square. I'm getting a 0.015625. Don't do any roundings over here, ideally, otherwise you'll get an inaccurate answer. Each of these values is being squared by placing them into this function over here. 0.375 times, you're getting a 0.140624, and I'm going to start writing these a little higher so we don't get cut here at the bottom. 0.625 square, I'm getting a 0.390625, and then last one, 0.875. 0.875 square, I'm getting a 0.765625. It's almost cut over here, but we can still see it. Now look over here. The limit of this Riemann sum that we're trying to calculate, ideally as n is always approaching infinity, though here n is really approaching 4 because we only went up to 4, and your first sum is always representing the item number 1 going up to n. You know you have to do f of xi times the delta x. You have to do the cumulative sum of all of these numbers and multiply them by your delta x, which is this 0.25. So let's do that. Let's add all of these 4 numbers, f of xi's, and we multiply them by 0.25, and we'll get our final Riemann sum, which will represent the area under this curve using the midpoint values. So we're going to add these values here. 0.015625 plus 0.140625 plus 0.390625 plus 0.765625. I'm getting a cumulative sum over here of 1.3125, which must still multiply with the delta x, which is 0.25. And let's do that. When we multiply this by 0.25, what do we get? Times 0.25, I'm getting a 0.328. This is what my answer is, 0.328125. Now there's a check for these type of questions. If you knew how to do integral calculus, or you knew the schematic for this, if you did the actual integration of this x squared from 0 to 1, this is what you would get. And you know you have a dx over here, you'd get x cubed over 3, and you do this over the definite integral interval you have from 1 to 0, and your answer would be 1 over 3. And you know when you do 1 over 3, you're getting a what? You're getting a 0.333 repeating. That's what you're getting. But look, we're kind of close to it. We have 0.328125, but the true value is 0.333. The area under this curve from 0 to 1 is a 0.333 repeating. But we're getting a calculated Riemann sum value of 0.3288125. Why? Because as n is a small number here, we used only 4 approximation rectangles. If you had used like 100 or 1,000, we would have gone very close to this 0.333, and we would have had a very accurate answer. Now hypothetically, if we had been using the right and the left endpoints, well, how would our question differ over there? I want to make some space over here, and I show you what approximations you would have used, or what values you would have used in terms of your intervals. Look over here. If you're using the right endpoints over here for the same exact question, your interval would be no different than what it is. It would still be 0 to 0.25 because you still have 4 intervals. The only thing that would change over here would be your xi values than what you input over here. Your right endpoints would be these. It would be 0.25, it would be 0.5, 0.75, and it would be 1.0. Then you would put these into x square over here to get your f of xi values. And these values over here is where your differences would arise, and then this entire calculation would be overestimated. If you're using the left endpoints, your specified values would be all of these sides over here. You'd have 0, you'd have 0.25, you'd have 0.5, and then you'd have 0.75. Then you would put these in, and you determine the f of xi here, and then you'd end up having a Riemann sum which is underestimated. Always best to use the midpoints because they give you the most accurate. And think of it like this. If you're looking at this interval over here only, this interval over here, and I'm going to draw the rectangle here, the left endpoint will be represented by the 0 value, the right endpoint will be represented by the 0.25 value, and the midpoint value will be right here, 0.125. So you have to decide, are you going to use the left endpoints, you're going to use the right endpoints, or are you going to use the midpoints for each of these? And I'm telling you the midpoint for each of these intervals. What are your interval numbers? Always go with the midpoint in numbers because they give you a more accurate representation. Using the left endpoint values, you've gotten a very significantly smaller number than this. Using the right endpoint values, you've gotten a much larger number than this. Using the midpoint values, you get a number close to the true area under the curve. We're going to close this video with these following summation points. When we're talking about integrals, we're talking about the area under a curve, and the limit of these values represents the area under a curve. We're basically calculating area in terms of x. We're looking at a lower limit, the interval from a lower limit to a higher limit, and we're putting the integrand into our calculation. But I haven't talked about actual integral calculations or integration yet because I've been talking about Riemann sums. And you know, Riemann sums, you can represent it by this capital R with the number of intervals. What we talked about today was pretty much basically for any kind of function. It didn't have to be even a parabolic function. Let's just look at this. And this is just example. We could have drawn rectangles over here, and I'm looking at these midpoint applications. See the midpoint, the rectangle is going through the curve at the midpoint only. The more number of rectangles that you can draw, the more the better. Alright, the more number of these rectangle values you can have, the better it is. Using midpoints is better. Using the midpoints is always better than using the right endpoints and using the left endpoints. Why? Because it'll give you a true representation or a more closer representation of the real area under the curve. And when you're talking about areas, you have to do individual calculation of each of these areas. Each of these areas has a width which is represented by delta x, and each of these areas has a length. Now the length is really represented by this value right here, f of xi. But you know, this xi value over here is what you're using as your specified value, right? So the length times the width will give you your area of each rectangle. You have to add the area of each rectangle, which would be a cumbersome process, but we have this Riemann formula which solves that. According to the Riemann formula, the width of each rectangle that you have assumed based on your interval is always equal to your upper level or upper limit divided by minus the lower limit divided by the number of rectangles you have. You know, the Riemann formula, it follows this schematic where limit as n approaches infinity. You're using a summation formula. Basically, the sum of the individual lengths where you've placed the xi or your specified value into your function and you've gotten the lengths. The sum of those individual lengths multiplied in the end by the width. You can do individual length times width and keep adding them up, or you can just add up all the lengths values and then multiply them in the end by delta x, and I've shown you that technique works. And that's pretty much what we're talking about in the Riemann sum. And always for each curve you can do left endpoints, you can do right endpoints, look over here, right endpoints only, right endpoints, or you can do midpoints, and midpoints are the best. Midpoints are always best. Left endpoint values for each interval will give you underestimation of your area. Right endpoint will give you overestimation of each area that you're calculating. And the schematic of these type of questions that I've shown you is this. You want to always start by determining, or the question will determine what your n value is, what Riemann sum you're calculating up to. Is it R5, R6, R4, or R3, or R2? But the higher the Riemann sum, the more accurate value it is. You want to start by seeing what this value over here is, right here. Then you want to start by doing this one next. Then you want to see, based on this, how many intervals you have. You're going to lay it on into this way. You'll have an interval over here section. Then you'll have your xi value, which will either be, you can say left endpoint you're choosing, or your midpoint, or your right endpoint. And then you're going to take this value for each interval and you'll calculate its f of xi, which you determine by putting the specified value into the function and you write it out. Here's your interval 1, 2, 3, whatever they may be, and here's your value which you're specified, and then you're getting these. You're adding up all of the sum total, and then you're multiplying it by your delta x to get you your Riemann sum. And that Riemann sum over here will represent the area under the curve. Not such a difficult process, because this Riemann concept is not difficult to understand. Again, the more number of rectangles you have, the better, because the more true representation you'll have to the true area. And remember, as I was talking about the rate of change videos, I showed you different techniques, which are the longer, harder techniques. And at the end, we had the derivative concept, which simplified it so easily. Well, just like that, the Riemann process is a more difficult process, or it's a more cumbersome process, or elaborate process, you can even say, because you're actually learning the theory behind it, versus just using an integral technique or a template for a specific function you have, and you can do it in less than 10 seconds. So keep all of this in mind. I didn't present very many examples at all, because in this video we're only talking about the concept of integral with regards to Riemann sums. In the next videos we can get a little more into actual examples. I hope you enjoyed this video. Have a good day. Thanks for watching. Bye.